Okay, in the last video, we had worked with this curve, x squared plus 5 equals y, and we had considered a segment of it from x equals 1 to x equals 3, and then we rotated that curve about the y-axis. Here, in this video, we're going to rotate this about the x-axis. And when we generate a three-dimensional figure, when we integrate to find the volume of that figure, what answer do we get? And the answer to that question is, it depends on what technique you use. If you use the method of disks, or whether you use the method of shells. For example, when we're setting this up, if your region of interest is underneath this curve here from x equals 1 to x equals 3, is this your region of interest? Or, again, we'll sketch the curve out very roughly. Here it is. X is 1, x is 3. When x is 1, y is 6. And when x is 3, y is 14. Or perhaps this is your region of interest, going from this value of y of 6 to this value of y of 14. And we're going to rotate the curve about the x-axis. So be careful to see what the problem specifies. If this is their region of interest here, and we want to find the volume, as we explained in our introductory videos, then we would be taking vertical strips like this, and that means then in this situation we're working with disks. So this would be the disk method, in which case our corresponding volume integral is pi times the integral of y squared times dx. And in this case, x goes from 1 to 3. And clearly, y has to be expressed as a function of x, which it is, so that would be no problem for us. On the other hand, if this is our region of interest, then we would be drawing horizontal strips like this that are parallel to our axis of rotation, the x-axis. Now we're dealing with shells, so this would be the shell method. And with the shell method, the corresponding volume integral is 2 pi times the integral of x times y, and in this case it's dy here. Y goes from 6 to y equals 14. Now how do we get these two different integrals? We have introductory videos that explain how we obtain these in different situations. And this one here, we'll just set the volume up, the volume integral up, but it's going to be pretty straightforward. The volume integral will equal pi, the integral from x equals 1 to x equals 3, just setting up the volume integral now, of y. Now y has to be expressed as a function of x, but it is, it's right here, it's x squared plus 5, except we have y squared, so we're going to have x squared plus 5 quantity squared dx. So there's not much to the integral really. This would be x to the 4th plus 10x squared plus 25x dx, and you're integrating that from x equals 1 to x equals 3. And you can see that's not a difficult integral. You can almost do it in your head for each of these individual steps. And you do that and then crunch the numbers, taking values of x equals 3 and x equals 1 and doing the subtractions and so forth. And I think the volume element comes out to be something like 2,776 divided by 15 times pi. Again, we're trying to stress in this video here is when you have your curve and you know which axis you're going to rotate it around, then you have to decide, okay, now for my volume integral, do I want to set it up as a disk volume integral or as a shell volume integral? And again, that's determined by the region of interest. If in a problem it states the region is underneath this curve, between the curve and the x-axis, then that's the disk method in this situation. And that's the volume integral for it. And we derived that volume integral in one of our introductory videos. On the other hand, once you draw the curve, if this is your region of interest right here, and now you're going to go ahead and rotate about the x-axis, then you're drawing strips parallel to the axis of rotation. That's the shell method, and that's the volume integral that you use in that situation. And again, we derived this as one of our introductory videos. If you haven't seen the introductory videos, we recommend that you do. We think you'll find them worth your while. Before we close this video out, though, let's just take a look at this volume integral. We're saying b is equal to 2 pi times the integral of, we go from y equals 6 to y equal 14. This is x times y dy. So x has to be expressed as a function of y. So we go to here, we see x squared equals y minus 5. So x, that equals the square root of y minus 5. So this integral here would be, here we have y, and then we have the square root of y minus 5 dy. Now, how do we integrate this? If we call this part here du, let u equal y minus 5, du will equal dy. And let's see how we set this up then. We would have 2 pi times the integral. Over here we have y. This has to be expressed, the whole integral now has to be re-expressed in terms of the new variable u. When we go back to here and we see y, that just equals u plus 5. So this is u plus 5. Y minus 5 is u, so we have u to the 1/2. dy, that's just du. So there it is. Now what some people do is when they make this variable change here, and we have y going from this limit to that limit, they'll put new limits in for the new variable. I usually don't bother doing that. I just remind myself, y goes from 6 to 14. Because once I solve this integral, I'm just going to go back and plug y back in here, remember what our substitution was, and then take it at my normal y limits. So this, if we integrate this, here we have u to the 3/2, that would be u to the 5/2 times 2/5, and here we have plus, this is 5u to the 1/2, so we're going to have 5 times u to the 3/2 times 2/3, and everything gets multiplied by 2 pi. So look at this, well, what is u? That's u right there. So now we say this will be equal to 2 pi times this quantity. 2/5, u to the 5/2, that's y minus 5, to the 5/2 power plus 10/3, and this will be y minus 5 to the 3/2 power. And y goes from 6 to 14. And here again, it involves some number crunching. It's not as bad as what it looks actually, because if we put 14 here, we have 14 minus 5. That's 9 to the 5/2 power, or that would be 3 squared to the 5/2 power. That's 3 to the 5th, which I think is 81 times 3. So I think this is going to be like 243. And then we have y is 6. 6 minus 5 is 1. So that just gives us 1 to the 5/2 is just 1. And the same thing over here, we have 14 minus 5 is 9 to the 3/2. That would be 3 cubed. That would be 27. Minus 1 would be 26 times 10/3 would be 260 over 3. It's not that difficult to do. It just takes a while to grind through those numbers. And I think when you do that, you'll see that the volume comes out being equal to 2,752 divided by 15 times pi. What we're trying to do in this video is not concentrate so much on the number crunching, but as to the different types of volume integrals you can set up, and which kind of volume integral do you want to use. And again, it depends upon what the problem is asking. Here's the curve. It's going to be rotated about the x-axis, and if we're interested in this section of the curve, directly underneath it, between the curve and the x-axis, then you want to use the disk method, and that's your integral. On the other hand, if this is your region of interest, then you have to use the shell method as you rotate about the x-axis, and that is your particular volume integral. And again, we derived these in the introductory videos. Again, and if you haven't seen those, we do recommend them. We think they'll be worth your while. Anyway, that's it for this video. Come back and join us for some more videos, and we'll start considering different types of volume problems.